So, this is Chem 30, Thermochemistry podcast. The first one, we're going to go and talk about molar enthalpy, enthalpy changes, and calorimetry enthalpy. We'll go into Hess's law later. But for starters, we can start on page 487. Number 6. So, in any calorimetry question, we know that Q is equal to MC times delta T, where Q is equal to the enthalpy, or delta H, of the reaction, and M is equal to mass, C is equal to specific heat capacity of the particular element that we're using or compound, usually water. And so we'd have a formula sheet to on page 5 to go and see what that specific heat capacity is. And T is change, that's what the delta means, in temperature. So, number 6 states, after coming in from outside, a student makes a cup of instant hot chocolate by heating water in a microwave. What is the gain in thermal energy if a cup 250 milliliters of tap water is increased in temperature from 15 Celsius to 95 Celsius? So, specific heat capacity of water is 4.19 kilograms per Celsius per joule, or joule per Celsius grams. Let's grab our formula sheet to verify. And it's actually on page 3 that we see our specific heat capacities, and we see water is 4.19 joules per grams per Celsius. And our mass is 250 milliliters, and we know that 1 milliliter of water is equal to 1 gram of water. And 250 milliliters of water is equal to 0.25 liters or kilograms of water. Therefore, our mass is equal to 0.250 kilograms. And our change in temperature is 95 minus 15, where we take temperature final minus temperature initial. And that would be equal to, we can just grab our calculator. And we can see that 95 minus 15 is equal to 80. And so we can go Q is equal to 80 times 0.250 kilograms in Celsius times our specific heat capacity, which we will convert into 4.19 kilojoules per kilogram Celsius. So Q would be equal to 80 times 4.19 times 0.25. equal to 83.8 kilojoules. Another one would be question number 7, and so it's another calorimetry question. Number 7 states, just move up. A backpacker uses an uncovered pot to heat 1.0 liters of lake water on a single burner stove. If the water temperature rises from 5 Celsius to 97 Celsius, what is the gain in thermal energy of the water? So very similar to the last question, Q is equal to M times C times delta T, where C is specific heat capacity of water once again, which is 4.19 joules per gram Celsius, where we can discover that our mass, if 1.0 liters we have, we know in conversion that would be equal to 1 kilogram of water. So we can just multiply Q is equal to 1 kilogram times 4.19 kilojoules per kilogram per Celsius times our change in temperature, where we're actually just going to write it out. 97, our temperature final, minus our temperature initial, Celsius, equal to, so we just put it in brackets, 97 minus 5 times 4.19 times 1 is equal to 385.48 kilojoules. And in proper sig digs, we'd realize that there's only the least amount is 2 digits of the 1.0 liters, if you're looking at the question again. So we'd have to convert our answer to 3.9 times 10 to the power of 2 kilojoules. Rounded. Lastly, we'll do another one, number 8, still on page 487. To test the efficiency of an energy transfer, a chemist supplies 30 kilojoules of external energy to a simple calorimeter. If 150 milliliters of water in the calorimeter is heated from 20.6 Celsius to 52.8, what is the efficiency of the calorimeter? So, this one's kind of different, talking about efficiency, which we know is what we get or what we want over what is expected times 100%. So, Q is equal to we'd have 150 milliliters of water, which we can simply convert to kilograms, to 0.150 kilograms, times our 4.19 for specific heat capacity of water, and then times the temperature, the change in temperature. So 52.8 Celsius minus 20.6 Celsius. Q would be equal to, we got 0.15 times 4.19 times, in brackets, 52.8 minus 20.6 equal to 20.237 kilojoules. Now back to the question, a chemist supplies 30 kilojoules of external energy to a simple calorimeter. So it's for the conservation of energy, what is expected is that 30 kilojoules of energy going into a system or whatever should equal 30 kilojoules of energy coming out. Now we know in any kind of system that nothing is 100% effective. However, we can go and calculate how effective something is by taking one of two ways. Even if we forget this part, we know that you cannot be 102% effective or 120. So we could try it one of two ways. We could go 20.237 kilojoules divided by 30 kilojoules times 100%. Or we could try 30 kilojoules divided by 20.237 kilojoules times 100% is equal to. So let's figure out the first part first. So 20.237 divided by 30 times 100 would be 67.5%. Whereas the other one would be 30 divided by 20.237 times 100, which would be 148%. Now we know that this is actually not what we're supposed to get. We're supposed to get 30 kilojoules and 30 kilojoules. However, we're losing it through some kind of defect in the experiment, some kind of endothermic reaction, or it's not a reaction, it's just transfer of energy. But somehow not all the energy is going into the system that we want, is going into the surroundings. 148% effective. If we're to use it this way, we know that can't be our answer. Can't be answer. If we're stressed out on a test, we could try out both of these ways and figure out which one is actually the way of doing it. You either know divide top, bottom, but determining should we have 30 kilojoules on the top or 30 kilojoules on the bottom, sometimes we forget. But if we do it, both are calculations, we can determine that this is actually our correct answer, 67.5%. If we turn to page 492 and look at question 12, we're going to look at a molar enthalpy change reaction. So the formula for molar enthalpy, or calculating it, is delta RH is equal to moles times the molar enthalpy of whatever we're calculating. N is our moles, and delta RH M is our kilojoules per mole. And once we multiply it, we realize that the moles cancel and you're left in kilojoules for our delta RH. Number 12 says, I'll just move it over. Predict the energy change for the combustion of 100 grams of methane in natural gas water. And it shows that CH4 is equal to negative 802.5 kilojoules per mole to produce water vapor. So, all we're trying to determine is how many, for 100 grams, how much are we getting in energy? So 100 grams would be, and all we gotta do is simply realize that CH4, we just have to find the N, because we're not given N, but we can simply calculate that. So CH4 is a combination of 1 carbon, so 12.01, and 4 hydrogens of 1.01. So together should be like 18.05 or something like that. So 1.01 times 4 plus 12.01 is equal to our grams per mole, but 1.01 times 4 plus 12.01. Oh, it's 16.05, sorry. Grams per mole. So now all we do for N is realize that N is equal to M over molar M. So N is equal to 100 grams divided by 16.05 grams per mole. So how many moles do we have? And all we do is go 100 divided by 16.05 to realize that we have 6.23 moles. Now we'd go 6.23 moles multiplied by our negative 802.5 kilojoules per mole. The moles would cancel, and we'd be left with times negative 802.5 is flat negative 5,000 kilojoules of CH4 when 100 grams combust. Number 13 is another molar enthalpy question. So we can just write out our formula. Delta RH is equal to moles times delta RHM, which is our molar enthalpy. Methanol is one type of fuel that is used in fondue heaters. In an experiment using a simple tin calorimeter, 2.98 grams of methanol was burned to raise the temperature 650 grams of water by 20.9 Celsius. Using the evidence, calculate the molar enthalpy of a combustion of methanol. So, we actually have two parts going on in this question. We have, instead of it actually equaling delta RH, or still delta RH, we know that this is actually also equal to Q, which is our MC times delta T. So, we need to realize what gets our delta RHM and what gets our MC delta T. In fact, we might actually have 2M times C times delta T's. Because if we wrote out a picture, what's going on is we got water inside this tin can being burnt by the combustion of is it methanol? Right, methanol. So, in a combustion, we know that this part of the equation has to be an actual reaction. So we'd know that this is CH4. Where this MC delta T, all it means is some kind of heat is being transferred. There's no reaction, or it might be getting heated up by a reaction, like the combustion of methanol, but they are not undergoing a reaction. All they're undergoing is some kind of increase or decrease in heat. So we'd have water plus tin can. So we can just, some people won't know what the specific heat capacity of tin is or have it memorized, and all we'd have to do is turn to page 3 in our data sheet and realize that it's 0.27227 joules per gram Celsius. So we'll write that out. 0.2 joules per gram Celsius. And we know water to be 4.19 joules per gram Celsius. So if we read over the question again, methanol and one type of fuel that is used in the fondue, an experiment using sample tin can calorimeter, 2.98 grams of methanol was burned to raise the temperature 650 grams of water by 20.9 Celsius. Now we're realizing that all it wants us to do is calculate really just for water. But instead, I'm actually gonna change the question and give the tin can an actual mass. So let's give it like 2 kilograms. So the mass of the tin can is 2 kilograms. So all we'd have to do is make it part of our question. So first, to find the combustion molar enthalpy of CH4, we have to find the moles. So we're given 2.98 grams of this methanol gas or liquid being combusted. We'd divide it by our m over molar m. And we know from the last question that it was 16.05 grams per mole. So 16.05 grams per mole. We'd realize we'd have 2.98 divided by 16.05 equal to 0.186 moles. We times that. Oh, we actually don't know the molar enthalpy. So we're actually trying to find this. However, through this question, we can go and figure that out. So the mass of water is 650 grams, so that's 0.65 kilograms times 4.19 times our change in temperature. And what I'm going to do is actually bring that out, or I can just write it with it. 20.9 Celsius plus our mass of our tin can, which is 2 kilograms, times 0.227 times the same temperature, 20.9 Celsius. All we're going to do is move over the moles and divide it by 0.186 moles to figure out what our delta RHM. Divide it here, cross it out, and figure out our delta RHM, which is our molar enthalpy of the combustion. So we're going to have 0.65 times 4.19 times 20.9 plus, in brackets, 2 times 0.227 times 20.9 equals 66.4. Now all divided by 0.186 moles. Realizing that our delta RHM for 2.98 grams of methanol being combusted, we have 357.0 kilojoules. So all that goes on in these types of questions is that something loses energy and something gains energy. As someone loses, someone gains. As the methanol gives off heat exothermically, endothermically, the water is absorbing this heat. So, if we were talking in perspective of the methanol, we'd say delta RHM is negative 357.0 kilojoules. So, we're going to look at page 494. And we're going to look at question 4 for another molar enthalpy question. So it reads, decane, which is C10H22, and they give us that, is one of the 100 of compounds in gasoline. The molar enthalpy of combustion of decane is negative 6.78 megajoules per mole. So we'll write that down. Delta RH is equal to, or delta RHM for molar enthalpy is negative 6.78 times 10 to the power 3 kilojoules. So all I did is realize that megajoules is joules times 10 to the power 6, but to leave it in kilojoules, we just times it by 10 to the power 3. What mass of decane would have to be burned in order to raise the temperature of 500 milliliters? So we got water, mass of water is equal to getting kind of unfocused. 0.5 kilograms. Our temperature, change in temperature, is 55.0 Celsius minus 20.0 Celsius, which is just equal to, or just simply go 55 minus 20 to equal 35 degrees Celsius. So we'll write out our delta RH M times moles is equal to M times C times delta T. So we know this is what is going to be reacting. So that's our decane. So decane combusts, loses energy, is equal to water gaining energy by being heated. So this would be our negative and this would be our positive. So what we're going to have to do is find the N inside this question. We're already given everything else to figure out what N is. So all we're going to do is go the mass of water, 0.5 kilograms times 4.19, the specific heat capacity of water, joules per gram Celsius, times our change in temperature, 35 Celsius, is equal to N divided by, so just bringing this over delta RHM, negative 6.78 times 10 to the power 3 kilojoules per mole, leaving us with moles, because this would be kilojoules on top, kilojoules on the bottom, leaving us with moles. So we go 0.5 times 4.19 times 35, all divided by negative 6.78 times 10 to the power 3, equaling negative 0.01081 moles. Now it asks us, what is the mass of decane to produce this heat transfer? So all we're going to have to do now is realize that N is equal to M over molar M, and figure out what our molar M is of decane is. And we just look inside our periodic table and realize that there's 10 C's, which have a value of 12.01. So 12.01 times 10 plus 22 hydrogens, which is 1.01 times 22 is equal to our molar and or moles per gram, molar M, times 10 plus 1.01 times 22, which is equal to 142.32 grams per mole for molar M. So N is equal to a negative 0.0108, or we can just cross out the negative because it's moles. So we just go N times molar M is equal to our mass, just multiplying. N is equal to 142.32 grams per mole times 0.01081 moles. Moles will cancel, leaving us with grams. 0.1081 equal to a 1.538 kilojoules. Or what am I doing? Kilograms. Write that again. 1.538 grams of decane. So we're going to take a look at page 501, question number 2C. And we're going to start to try to communicate molar enthalpy change in a reaction. So if we're looking at 2C, the complete combustion of pure carbon fuel is the change in combustion enthalpy molar is equal to negative 393.5 kilojoules per mole of CO2. So our molar enthalpy change in 1 mole of carbon dioxide, we'd know that there would be, in a combustion, negative 393.5 kilojoules being released. So to communicate this, slide this over. We have 4 ways of doing this. In fact, though, we have one already given to us, and that is our delta RHM is equal to negative 393.5 kilojoules per mole CO2. That is our first way. Communicating of our molar enthalpy is actually showing what our molar enthalpy of the compound that we're combusting or reacting. So the next part, we'd probably try to write out the combustion of, so that's carbon. So any combustion involves oxygen gas, so that's O2 gas, plus carbon. Is it solid? Yeah. To form CO2 gas. Our next way of showing how, so all we'd have to do is do this and go O2 gas plus C solid to form CO2 gas, and then off to the side we go delta RHM is equal to negative 393.5 kilojoules per mole. So in what it's saying is, in this reaction we can determine that 1 mole of any of these products is equal to negative 393.5 kilojoules. So for our next way of communicating it, number 2 we'll call it, is actually writing it as a product. This negative means it's part of our products. If it was positive, it'd be shown as a reactant. O2 gas plus C solid to form CO2 gas plus 393.5 kilojoules. We wouldn't write negative because as we're writing it, part of one of our reactants or products, we never show it as minus 393. I guess we could move it over here and go minus 393.5. That's just not very proper or the way you're expected to show it. Our third way is saying, what is our delta RH? And our delta RH of this question is actually what we wrote here, delta RH. Sorry. This would be the first way. This would be the second way. There's really no numbering, but whatever. The first way would be our molar enthalpy and just saying what they show us. Our second way is writing it as a delta RH. So it's saying that in this particular reaction, 1 mole of carbon dioxide is equal to negative 393.5 kilojoules, along with carbon and O2. However, if we were to have it as a 2, as we'll see in later, say I were to write it like this, O2 gas plus C solid, so 2, 2, and double everything, I would have to say our delta RH of this reaction is negative 393.5 kilojoules times 2. Our fourth and final way of communicating molar enthalpy is an EP graph. And all you do is show EP in kilojoules and write reaction process going this way. EP graph of combustion of C carbon, pure carbon. So we write it anywhere on this line, and we'd go straight line, O2 plus C solid, O2 gas, through reaction. And since this is exothermic, because of this negative, we'd show it below our reactants and show our products to be CO2 gas, saying that this part would be 393.5 kilojoules. The difference between our products and reactants is 393.5. And this showing that it's below shows us that negative of this reaction. So this would be considered exothermic. If it was endothermic, we'd see an EP graph of some kind of reactants with their products being above our reactants. So that'd be EP Rex process. And this would be the change in delta RH of our reactants, our reaction. If we look at 3A on the same question, or the same page, that is page 501, it says, for each of the following balanced chemical equations and standard enthalpy changes, write the symbol and calculate the standard molar enthalpy of combustion for the substance that react with oxygen. So these are all combustions, they're saying, with oxygen having different molar enthalpies or enthalpy changes. So what happens is in 3A, they're saying 2 moles of H2 gas, hydrogen gas, plus oxygen gas react to form 2H2O.